Hello, community! We have some brand new research from UC Berkeley, Stanford, Databricks, and MIT, and we have a new genetic algorithm for artificial intelligence. Let's have a look. GEPA. And they tell us this new algorithm is better than reinforcement learning, more efficient than reinforcement learning, GRPO, and it has a better performance than DSPy. How is this possible? Well, it is all about a reflective prompt evolution that can now outperform reinforcement learning. This is absolutely fascinating. And you know the time when DSPy was prompted here, not as a prompt optimizer, but as a prompt programming regime. Now we go the next step, because it is the creator of DSPy here, Omar, originally from Stanford, now at MIT, who supervised here his team for a new genetic evolution for AI prompts. Absolutely fascinating. So let's have a look. July 25, 2025, we have here a new study, GEPA, Reflective Prompt Evolution, and genetic evolution here that can outperform reinforcement learning in AI systems. Databricks, MIT, Stanford, UC Berkeley, BespokeLabs, and Notre Dame. And we have 82 beautiful pages full of formulas and numerical tasks and everything. But I want to give you the main idea that you can enjoy this paper when you read it for the very first time. We have GEPA is a genetic Pareto optimizer. So you see, we have here this idea here of a genetic pool that we optimize, and then a Pareto frontier that we will investigate. When we are back to a prompt optimizer, we're not prompt coding, we are not prompt programming. It is just a prompt optimization now on a much higher level. So let's have a look at the result. Is it worth that you read the paper? So, of course, you have to be familiar with my video on DSPy, with my Pro version 2, optimize it, that they use it. And GEPA now goes here on a system level. You see, we operate now with system level trajectories. So we have the reasoning traces, we have all the tool calls, we have here the logs from the tool calls, the tool output and everything. But now the interesting thing is we have a look at natural language to diagnose the problems, to diagnose the purpose, all the updates, and have here a Pareto frontier. How they do this? Well, beautiful is at first, compound AI system. So agentic, multi-agentic, tool use, whatever you have here in your portfolio, you can use this new methodology to optimize your system performance. And let's have a look here if you should use it. Here you have the number of rollouts here with reinforcement learning with GRPO, the classical 24K. And you see, okay, on a particular score, I reach here, let's say here, this, a plateau. DSPy with a MyPro version 2 is here in green, and you are much better performance, and you see you don't need as many rollouts. But look at the new method, GEPA. Have a look at this. Pareto optimal frontier optimization via a genetic algorithm for AI. If you're not familiar with this particular benchmark, hover here with a Q13, 8 billion free-trainable parameter model, so a rather small 8B model. But what is Hover? Well, here you have a dataset for many hop fact extraction and claim verification here. This is here a verification dataset built on the Wikipedia corpus. Great, you have everything available for you, free of charge. Absolutely fantastic. And now they say, you know what? Compound system, multi-agent system, you have scaffolding techniques like React, everything that we know. We can use this methodology. Let's go. So, they say, hey, for adapting LLMs to downstream tasks, in the classical way, we use here reinforcement learning. We have verifiable reward structure. One of those algorithms is a group relative policy optimization, GRPO, that you know. And you say, what is the core? The core is that we have here a reward coming back at the end, And normally we have a scalar reward that observed at the end of each rollout. And these rewards that estimate here the gradients for the policy improvements. Great, but this, as I showed you, requires tens of thousands rollouts in practice to fit to new tasks. So if you want to train your LLM to new tasks, to new challenges, to new complexities, you need 100,000 of these rollouts. Long time, high infrastructure, very expensive. Just think about a Q13 model, an 8B model, GEPA outperforms GRPO here up to 19%. while requiring up to 35% fewer rollouts. Sorry, I made a mistake. 35 times fewer rollouts. This means absolutely one-to-one. You have to pay less for the better performance. Okay, and GEPA surpasses here the previous state-of-art prompt optimizer like we've seen in DSPy with MyPro version 2, obtaining here an aggregate optimization gain of 14%, more than doubling here the gains achieved by MyPro version 2. What an absolute beautiful idea and methodology. Now, you might say, hey, can you just summarize MyPro? A Bayesian optimizer explores the prompt space by trying different instructions, a few short examples, a probabilistic model of what kind of prompt seems to work, and uses this model to suggest the next candidate. Yes, but we have something better. This is now an evolutionary optimizer. This is a genetic pool optimizer for an AI system. It sounds crazy. It is absolutely crazy. And yeah, it's a little bit of marketing, but I will show you in detail what it really means that you have the basic understanding and then the complete idea. It doesn't just try now GEPA to optimize your different predefined options, because the power of this new methodology is it creates entirely new strategies through a self-reflection. So this key is here reflective mutation mechanisms. And it's unbelievable that this idea here from genetic works suddenly in artificial intelligence. And we will generate here child prompts, so next generation prompts, but they are not just a variation, they're not just a pattern modification, because we will need here a new LLM, and this will generate here a complete new hypothesis born here from the understanding of a very specific failure. So unfortunately, and this is one of the main drawbacks, we need here a huge master GPT, like GPT-5, or I don't know, Gemini Pro 3. And then there's the second innovation in this paper, because you want to have a broad gene pool. No, you don't know how the complexity level will increase. So you don't want to have just one or two specialists. No, you want to have a broad frontier of specialists. So here we have the Pareto-based selection that maintains here a diverse frontier of specialists. And I will show you how we will calculate here the scores for each specialist and how to select those group of specialists for the perfect team when we have here a complex, multifaceted task. And this is really elegant and simple. Now, of course, DSPy was not the last. I had here a video on TextGrad, or if you really want to go the next step here, beyond DSPy and TextGrad, we had here PDL in this particular video. If you're interested here, an alternative, if you want, path forward. But let's have a look at here the very latest just published yesterday. What is the main idea? Just notice that the primary focus here of this new paper here is also the sample-efficient adaptation of AI systems to new tasks. Preliminary findings suggest, if you have a closer look, especially then at the annex of this paper, that GEPA, this new methodology, has also here promising results on the inference time search technique. So not only do we train here our multi-agent system better in the training, but we also have here a test time optimization algorithm we could apply at inference time. This makes it so much more interesting. If you want to see this, it's a little bit interesting here from the original paper from MIT, Stanford, and everybody. This is here the reflective prompt evolution. This is here part 1 of the idea. And if you want to see this in a pseudocode, this is it. But if you're new and you want to say, hey, just give me the basic idea, this is what I want to do in this video. So, at the heart of this paper, it's a simple idea. You say, I want to have a transformative idea that will really challenge today's guiding reinforcement learning paradigm for the agent optimization. And what I say is, hey, listen, we have a language model. So guess what? It's nice to calculate here reward models, so another LLM, where I have a numerical policy optimization that is guided here by, let's say, a scalar rewards function that propagate back and optimize here the complete system. But you know what? I have a language model. So damn, why don't I use this power and I strengthen a strength and I go here with a reflective, language-based self-correction methodology. And the authors found that this is a real powerful idea. So we use here the LLM's own capacity, arguing and input-output in language here. And let's say we have a reasoning capabilities in our LLM. We need a rather huge LLM for this. How to utilize this very fact. So instead of treating here an agent as a black box to be tuned with numbers here on gradient optimization, we should treat it here as a kind of a reasoning entity that can understand its mistakes and articulate a better plan going forward. In essence, GEPA is here, if you move here from a statistical correlation to a causal diagnosis perspective, just two elements. The reflective prompt mutation, this is the genetic part, and then the Pareto-based candidate selection. This is, if you want, genetic optimization of a genetic pool on a frontier that we define as the best hypersurface. So GEPA in itself is now, quotation marks, structured as a genetic algorithm, but think more like an analgon. No, it's not really a genetic algorithm. We just take some basic ideas from population dynamics and implement it here in artificial intelligence. Let's have a look. Reflective prompt mutation, the mechanism explained in simple terms. We just need 5 things. We need the prompt of the parent, so this is the current set of instruction. This is the code, the buggy code that we want to improve on. Then we need here the execution traces, so not the reasoning traces, the execution traces. Those are all the details logged from running this here on few examples. So every step that the agent took, the input, hopefully we have an open source model where we see the internal sort processes and the internal reasoning traces here, like a QN3 model. And this is why Stanford MIT used the QN3 and not a proprietary. They also use the GPT 4.1, but the insight we get here from the free models, all the tool calls that it did, everything, and the final output. All the tool results here, intermediate results. So we need everything from the logs. And then we need a feedback function. It's not just a score. It provides here a specific natural language reason for the failure. Let's say something went wrong, and now we want to understand, hey, I have an error message. Think about coding. No? You got a very specific error message for a very specific error. And now you use this, but you don't use it here as a scalar single reward function at the end, but you say, hey, wait a minute, I have the ability to talk, have here a linguistic pattern recognition. So let's use this. So what we do is we have here another, the big brother, the meta optimizer, a senior LLM. Let's say GPT-5, hopefully it's already released when you see these videos, whose job is now to reflect on this particular error, given the context of everything that happened, all the logs, all the internal reasoning traces, all the tool calls, all the tool results, and whatever. So this meta optimizer has now a crucial instruction template that we give to the optimizer. We call the meta prompt, telling here the senior LLM, let's say GPT-5, exactly what to look at and what the goal is. So we need here a superior, let's call it a super intelligent AI that looks here at a student AI, the first 3 points here, and tells the student AI not a reward structure, but the details in a linguistic causal reasoning trace, reflecting on a particular error it gets back. That's it. Come on, this is simple. So let's walk through one cycle of this reflective prompt mutation using here this very simple analogon. You have a senior developer, and a junior developer. Never mind what it is. So the first step is the junior developer, it simply fails at the task. Ne? So you give him here a parent prompt and an input task, and it executes here the junior. And the junior produces here an output. Unfortunately, we see it's not working. So next step is then to gather all the evidence. No? We collect all the full execution traces, as I just told you. We run a feedback function to get a precise error message. If we do this in code, you immediately understand what it is, but we get the same error message back in a linguistic semantic structure. No problem at all. And now we initiate this reflection session, this code review session. Now I assemble a meta prompt. And this is, if you wonder where the magic happens. No? So we present all the evidence that we have and all the failure or whatever to this meta optimizer, to GPT-5, to the senior developer, to your boss, if you want, in a very structured way. Because this meta prompt looks something like this. For the meta optimizer, we say, hey, you're an expert in improving AI instruction. I have an assistant here that is failing here on a particular task. This is the instruction I gave here to the student. Here, really, the contents here. Here is what happened when it ran this. So here the complete logs that are available, input, execution, trace, and output. And here's also the specific error, the failed test. And now I tell GPT-5, for example, hey, your task is now carefully analyze the failure, understand the complete context in what this happened, understand the complete linguistic, semantic, code-based, causal reasoning environment that we are operating in on a domain-specific knowledge, and then write a new improved instruction that fixes this error while keeping the parts that worked intact. So real close to code debugging, but now on a linguistic level, because we say, hey, we don't need this really expensive to run and tens of thousands of rollouts here for reinforcement learning. We can do this utilizing here the language capabilities. And now the meta optimizer GPT-5 reads the entire prompt. It connects the dots, if you want. GPT-5 says, aha, the instruction was maybe too general. It didn't account for a specific edge case mentioned in the feedback and whatever. So it understands why the error happened, why in this context, what is the root cause. And then the meta optimizer GPT-5 writes now a new improved prompt. This is not a child prompt. And you see here the genetic idea of genetic pool comes in. And this new prompt is now not a new combination of known elements like DSPy, but this is now, given the superior super intelligence of GPT-5, a mutated version of the parent. So it can happen. It's not just a small random chance of a known modification, of a genetic modification, but it can be something completely new. Out of the domain, out of the distribution, out of the probability sequence. And this is, if you say, hey, whatever genetic modification could theoretically happen in the real world, we have no idea. It can be, 3% deviation or 27% deviation, completely out of this world. So you see, this is this idea of a genetic algorithm that is rather simple to implement here in my simplification of these 82 papers. Why is this now so powerful? It simply moves beyond this what we have, this correlation up until now, to a stronger focus on the causation. What is the root cause here for this particular failure? You have a high level abstraction. You go and you use the power of logic, of causal reasoning of an LLM. And you don't say, okay, now I build a reward system and I will have millions of tensor weight in the multiple layer of the transformer. And I will have to perform millions of numerical operation if I have now a modification. You see, we use now a much smaller but a much more meaningful search space if we operate not on numerical tensor weights, but in linguistic logic sequences. Sample efficiency, each mutation is an intelligent guess based on a rich diagnostic data. So massive improvements can be done with just a simple example of a single failure. You just have to see one failure to understand this could just be a representative of a class of thousands of mistakes that could happen. You just fix here one algorithm and 1,000 potential follow-up mistakes or simply erased. And of course, beautiful, We don't need here to understand tensor weights on a numerical level. We just can read it. We literally read the history, how the agent learned to handle different scenarios. Perfect debugging, perfect transparency. If you use an open model and not a closed-up proprietary GPT-5. This was the first part. And now to the Pareto-based candidate selection. This is now where we have Pareto frontier optimization. You know, optimization, every optimizer has the same dilemma. Exploration versus exploitation. Exploitation is simple to explain. You find something that works well, one solution, and you stick with it and you try it even better. No? But you are on a very single drill down. You go down deeper and deeper, but you don't look here. Hey, is there any other possibility where I could start to drill and find here another minima? Exploration, you go in the width. You don't say, hey, I have an extreme focus on a very narrow set. No, you say, hey, maybe I missed something completely different. Yeah? I have to explore the available space. And GEPA's core idea here is rather simple. You don't want to find a single champion, no? But you understand that if you have higher complexity problems, you have, in your quest to reduce the complexity and generate multiple lower dimensional problems, so you need now not one specialist, but you need now a frontier of diverse specialists for each of those subproblems. Yeah? Maybe you have a team of 10 agents, 20 agents with their LLM incorporated for an AI agent. Yeah? Now, the interesting part is you don't go always for the best specialist in your field because those agents are interacting and form, if you want, a team. So you have something like a human team dynamic if you did it in a right integration. So there is now something interesting happening. Let me show you an example. If you have a greedy operation, or manager or algorithm, looks at all the resumes here from all the potential team members and hires then the single person with the highest possible score in a single category. So record holding PhD student for control system theory. And then they just hire around this singular person. They build a team around this singular expertise. Now the resulting element, if you have a complex system, is great because then the object will have this singular performance, but all the other things will just fail to be optimal. So the whole project will fail if you only have one genius and all the others are not really up to the task. So what is the perfect team? The GEPA manager now tells us here the breakthrough could come from any of your frontier team of experts. So you have to keep them all engaged, fostering collaboration, and drawing here on the ideas for a diverse strength profile. So you kind of evaluate the pool. And you have to generate a pool, I'll show you this, and then you evaluate the pool for very specific task profiles. No? So in each generation, GEPA now runs all its current candidate prompts on a different set of tasks and just scores here each prompt on each task. So it knows exactly how everything is doing. And then you identify the Pareto front, or in my simple example, you hire now the elite team, but not the single best person and build a team, but you hire a different elite team for different low complexity tasks. No? So you have now a filtering. So algorithm iterates through every prompt and asks you a simple question. And this is here brilliant. Have a look at this. The question is there any other prompt in the pool that scores higher than this one on at least one task without scoring lower on any other task? So nice. So if the answer is yes, the prompt is dominated and it is temporarily ignored because there's somebody better. If the answer is no, that prompt is non-dominated and is added now to the elite pool, our Pareto front. Now we have a lot of specialists standing here at the Pareto front waiting to be deployed. Then we have a stochastic selection. If you want a weighted lottery, so instead of just picking here the best from this pool, GEPA now, and this is the idea, holds a weighted lottery to select here a parent for the next genetic mutation in the development of the prompt. So each member that's standing now at the Pareto front gets a number of lottery tickets proportional to their score. But remember, we have to explore or balance here exploration and exploitation here in a sensitive balance. No? Let's look at this exploitation. The more balanced and the more high-performing candidate get more ticket and more likely to be chosen. An exploration, these are the specialists, this single peak specialist. So even if the average score about multiple domains is lower, they are still standing here at the Pareto front and holding their tickets. They still have a chance to be picked. So they can be selected, preserving now their unique genetic material, their specialization in this population, in this subpopulation that is standing at the Pareto frontier line. So you see, we don't have from all the things, then we say, okay, one winner. This is here the specialist for control theory, I think it was. No, you keep your pool of potential agents, of potential specialists wide, because your task will be a high complexity task that you will subdivide into multiple lower complexity tasks. Therefore, you need specialists for all of them, but you need specialists that are not a single peak specialist, but also know from the other domains. So you want the best team structure, not the best single player. You see, it's easy. Let's do just give you here an example. Let's do here this experiment. Let's say we have a complexity and I subdivide the complexity in two lower complexity structures. One is mathematics and one is writing. So two domains, great. So now here I have my specialist. Let's say I have 4. I have a pure mathematics specialist, scores 95% in math, but only 50% in writing. And then I have a writing specialist, guess what? 92% in writing, but only 55% in pure mathematics. And then, hey, have a look. I have a generalist that has 80 both in math and 80 also in writing. So you see, it has not the peak performance of the pure specialist, but in a team that depends on a co-evolution of math and writing, this looks interesting. And then you have another one, and look, also 70-70. So above the 55 or the 50 here of our specialist. So how is this mechanism now working? Now, in the worst case, in the traditional case, we have a greedy optimizer. Just look at the highest score, select the highest bidder, this is it. So we go here for 95 is the absolute maximum in all the data field. So we go with this mathematical specialist that has no idea about writing. So if you will read the final report, the writing, you only have a very low performance, although the mathematical ideas presented in the paper are genius, but this person cannot formulate it in a way that the audience would understand it. Sometimes happens to me too, I know this. But let's look at the new methodology at GEPA, the filter. Let's go step by step. So the first 95-50, is there any other prompt that has a math score that is high as 95? No. So we put him here on the front line, so it's in our pool. Second one, is writing here 55-92 dominated by anybody else? No other has a higher writing score than 92, so we put him also on the line. It's in our genetic pool. Now, interestingly, 88, this balanced expert. P math is better at math, but worse at writing. And P writing specialist is better at writing, but worse at math. So, therefore, no, it is not dominated. So we take this generalist also in our genetic pool. But now the filtering happens, and I've chosen this example that you see. 77, so there are in some subdomains better than the specialist for writing and better than the specialist for mathematics. But now, given our particular query, we have to answer, yes, this particular agent is dominated by somebody else, by P balanced. Therefore, we do not put him in our genetic pool because we have a better, let's call it a generalist, that has a higher score. You see, this is a simple filter mechanism. So what we end up with? We end now with our, in this first generation of genetic modification, if you want, elite pool here, our Pareto front, we have now P-mat, P-writing, and balanced 80-80 standing here at the Pareto line. Those are now in our pool, and now comes the interesting question. Who will be now selected from those three to be here the parent for the genetic mutation for the next mutation that hopefully is going to happen, for the next improvement here for our AI system? And as I told you, this simple system. We can calculate now different scores. We can weight scores. If you say, hey, in the task that I have, mathematics is dominating. So I give 80% of the score. I weight here mathematical excellence and only 20% to the writing, because he is not going to write here the end report, just some, I don't know, interim reports. Or you can say, you can weight it 50-50, whatever, you get the idea. Let's go with an average score here and let's do this. So 95, 50, 72, 55 and 92 divided by 2, 73. But look at our generalist, 80, 80. Wow. So this is what we need. If we say I need 50% math and 50% writing, we have a winner. This will be now the parent that gets here the access here to the next genetic modification. It will be this particular prompt, this particular specialist prompt for the optimization of prompt engineering, prompt genetic, prompt programming, whatever you like to call it. Why is this so powerful? It preserves the specialist in the pool. It is, if you want, mathematically guaranteed to protect our niche, our high-performant mathematical geniuses from being eliminated by our just good enough generalist. So this maintains here crucial genetic diversity, because maybe the next task has a higher complexity where we need 80% to weight the mathematical excellence of a prompt, and therefore we would miss here this prompt structure, this agent, if we would eliminate it here for lower complexity task, and we would choose good enough generalists only. It guarantees progress. It ensures that the population is always moving forward. As I showed you here, the fourth prompt was eliminated because the third one was better. So whatever you have a new entry into your pool of prompts, you will always choose here the best one. If a new best one comes in, it will be selected, and one of the old members of the pool will leave the pool. And a richer gene pool, a higher performance gene pool here of prompts, sounds a little bit crazy. Just think about here, it's an optimization process by itself. Forget about genetic pools. This is maybe just a marketing here for the next step, but it is just another optimization methodology. Plus, and now think, we are not going just with 2 subcomplexities. Let's say the success of the next task is multidimensional, that we need 10, 20, 25 reduction in complexity. So instead of 1 task with a complexity level of 25, we will have, if this is possible at all, it's just a Gedankenexperiment, we will have 10 complexity elements, maybe with a complexity level of only 2. So the more complex you go, the more powerful this methodology could become. And it outperforms every other method, as we have seen. I had the idea, so do we really need again, this monster, huge GPT-5 system, this Gemini 3, this non-open source model that needs, I don't know, 1,000 GPUs or 10,000 GPUs to run and execute your command? And unfortunately, if you think about it, yes, the functionality of the meta optimizer LLM in this flow, in this process flow, is essential. Why? Because it needs here to parse the complex technical execution traces, all the log, all the function calls, all the intermediate outputs, and understand here on these facts here the logic, the flow of the logic, the structure of the logic, and how to optimize this. So we have to have here a generalist, a huge generalist model like GPT-5 or Gemini 3 for the job. Because it must identify the precise point of failure in a long chain of documents of reasoning, attribute the error to the specific flaw. It must understand everything, and there's a non-trivial causal reasoning task that can only be done currently by our biggest LLMs. And it's not just that it has to fix the bug, no? It must also have the, let's call it the intelligence, the creativity, the insight to choose now a new set of instructions from the prompt that drives us forward and not backward. Clear, concise, robust. Do not introduce any new bugs, please. No regression at all. So this, unfortunately, we need, or maybe we depend again with this kind of a solution on a superior mastermind in AI to help our student AI perform, our open source students to perform better and better. I'm looking forward for a solution, whoever comes up with, that we can get rid of these huge LLMs like GPT-5 and can really work with open source LLMs. This would be a dream come true. So this kind of leads me here to a fascinating consideration I can call the GEPA paradox, because to efficiently and cheaply optimize a potential small or a specialized multi-AI agent system, you still need temporary access to large, expensive, and powerful generalist AI. So all of this methodology, as beautiful as it is, somewhere in the cloud, you must have your Google, you must have your OpenAI, you must have your Microsoft that have millions of GPU in the cloud able to perform this high complexity task. So you depend with your methodologies still on proprietary huge AI system. And this is what I do not like in this solution. But otherwise, this solution is absolutely beautiful. I give me only here the glimpse of the main idea. There are so many other technical details and mathematical details for the optimization that you find in those 82 papers. Please have a look at it yourself. It is absolutely interesting to learn. And if you would make the mistake to go here with a weaker LLM here for the meta optimizer, this would really be a false economy, undermining here the very mechanisms that makes here GEPA so powerful. So unfortunately, I thought about it. Is there a way out in this particular methodology to substitute GPT-5? But I could not find an alternative or a modification to this GEPA methodology. If you have an idea, please leave it in the comments. So I say thank you. Absolutely fascinating new research publication. A genetic algorithm as an idea for a further AI optimization for higher complexity reasoning tasks. If you enjoyed it, why not subscribe, and I see you in my next video.